In this video, we will further study the capacitors in DC circuits. The equation that relates the current and voltage of a capacitor is given here, where we say the current through a capacitor is I, which is equal to C times the rate of change of the voltage. Similarly, if we take equation 1 and if we integrate both sides, we can get equation 2, which gives us the voltage across a capacitor if we know the current. And these two equations actually describes how a capacitor will behave. For instance, let's say we have this capacitor and the direction of current I is given in this direction, and the capacitor voltage is, let's say, V. So the voltage between the two plates of the capacitor is V. And we have previously said that a capacitor can be compared to a bucket where we will pour water into the bucket, and water represents current over here. And this level of water in the bucket actually represents the voltage across the capacitor. So this is our simple comparison of a bucket and a capacitor. So the larger value of C if a capacitance is large, which will mean that our bucket is large, and so on. So the first thing that we want to discuss today, based on these two equations that we have, is that the voltage across a capacitor cannot change all of a sudden. Okay, so the voltage V across a capacitor cannot change abruptly. By this we mean that the voltage can change slowly as a function of time, but we cannot expect that a voltage was 10 volts at a given time and all of a sudden it jumped to, let's say, 20 volts. So that abrupt change is not possible for a capacitor, and we will look into that a little more. So let's say this is our capacitor, which is again a bucket of water, and the only way I can increase this voltage across the capacitor V is by pouring current into the capacitor or water. If we pour water, we know that the voltage will rise as a function of time, or if we take water out from the bucket, the surface of water level, that will slowly decrease, and which means which corresponds to a decrease in the voltage across the capacitor. So it can decrease slowly or it can increase slowly, but it cannot happen that at a given time the voltage is, let's say, over here as shown, and all of a sudden the voltage jumped to this point. This cannot happen. For this to happen, we will have to pour in an infinite amount of water very quickly. Okay, so the rate at which the water comes into the bucket would be infinite. So that cannot happen. Now let's see the equation that we have, which says I equals to C times dV by dt. Okay, I want to write it this way, that dV by dt is equal to I divided by C. All right, so this is C. Now let's see what we are trying to say over here. So let's say this is time and this is the voltage across the capacitor. What I'm trying to say is that, let's say this is the voltage across the capacitor and I'm looking for this kind of change. So you see, at this time, the voltage across the capacitor jumped from 0 to, let's say, 5 volt in a very short period of time, almost instantaneously. And at this time, the voltage jumped back from 5 volt to 0 volt, again in a very short period of time. So this abrupt change, a capacitor does not allow that. And we want to understand why does a capacitor will not allow this. We discussed this a little bit in the form of a bucket of water, which is a convenient analog between the two. But let's now look at this equation that we have and see if this equation will allow us to do this kind of abrupt change. Now, I want to see how much is dV by dt for this abrupt change to occur. Let's say the time in which the voltage increased from 0 to 5 volt is a very short period of time. So let's say that time is dt, and that is equal to, let's say, 1 nanosecond. Nano means 10 to the minus 9, so a very short period of time, so that's 1 nanosecond. And the voltage rise, we can see dV is 5 volts. So therefore, dV by dt is 5 divided by 1 nanosecond, which is 5 times 10 to the 9. Now that's a huge number. Now this is our dV by dt. So from our equation, this requires that I should be equal to C times dV by dt, or I can say that C times 5 times 10 to the 9, okay, ampere. So this much amount of current will be needed by the capacitor if we want to increase the voltage by only 5 volts in 1 nanosecond. Right, so that's a huge amount of current. We can assume some different values of the capacitor. For example, if I say that C is equal to 1 microfarad, then in that case the amount of current will be 1 micro, so that will be 5,000 amperes. Micro is 10 to the minus 6, so multiply that with 10 to the 9, so that will give me 1,000. So 5 times 1,000 is 5,000 amperes. So 5,000 amperes will be needed for a capacitor which is not very large. It's only 1 microfarad capacitor. A larger capacitor will even require more current. For an abrupt change to occur in the voltage of a capacitor, we will need infinitely large values of current. The power supply that I have, it can supply about 2 amperes maximum. So 5,000 is a huge amount of current. So therefore, we will say that the capacitor voltage cannot change abruptly. What can happen with the capacitor voltage is that it can increase with time, it can stay constant, or it can decrease with time, but it will always be kind of this continuous waveform. It cannot jump from here to here all of a sudden. This is not possible. Okay, so a capacitor cannot do that. So the voltage across a capacitor cannot be changed instantaneously. That's a property of the capacitor, which is based on the fact that the voltage across a capacitor is the integration of the current I. And by integration, we mean summation. The current keeps on coming into your bucket and you keep on adding more charge or more current to the previously summed value of the total current. So that's what the integration is doing. So that's the first point that I wanted to make today, that the capacitor voltage cannot change abruptly. Now, the second point that we want to discuss today is that a capacitor is treated as an open circuit for DC. We briefly mentioned it in the previous lecture, but let's see what we mean by this. So let's assume that I have a voltage source and I have constructed this series circuit of a capacitor and a resistor. My voltage source is 10 volts, so it's a 10 volt power supply. The resistor has some value R and the capacitor has some value C, and we will say that the current flows in this direction. So initially we will assume that the capacitor was not charged, so the voltage across the capacitor was 0 at t equals to 0. So I can say that Vc at t equals to 0 was equal to 0, so it was not charged. Vc stands for the capacitor across the voltage across the capacitor, and Vr will stand for the voltage across the resistor. Okay, so with this condition, if the capacitor is not charged, then this means that what will happen at t equals to 0. We want to see how will the circuit look like at t equals to 0, and you know that it should look like this, that I have a resistor and basically the capacitor, there is no voltage across it, so it looks like a short circuit at t equals to 0. And this 10 volts of the battery will drop across the resistor. So I will have 10 volts rise and 10 volt drop. And because the voltage across the resistor is 10 volt, I know the value of the resistance, so therefore I can find the current I, and the current I at t equals to 0 will be equal to the voltage across the capacitor, which is 10 divided by the resistance of the capacitor. So it will be 10 divided by R. Okay, so that will be the initial current that will flow in the circuit. Now you see, this is a DC circuit. We have connected the capacitor, but we are treating the capacitor as a short circuit, not as an open circuit, because at this time the capacitor is not charged and it is actually a short circuit. Now, when this current flows in the circuit, it will start charging the capacitor. So after some time, the capacitor voltage will increase because now a charge has acquired on the capacitor. So I will have positive charge on top and negative charge on bottom. I will erase these extra sign so that we don't get confused. So I will have some charge across the capacitor, and now the capacitor has charged to some voltage, not to 10 volts, but to some voltage. So let's say at some later time, which we do not know right now, but later we will calculate it. So let's say at some later time, t equals to t1, the circuit now looks like this. I have the 10 volt supply and the resistor, and now across the capacitor, I have a voltage drop of, let's say, 3 volts. Okay. So the voltage drop is 3 volts because I got this capacitor partially charged, not completely charged, but partially charged. So we had 10 volts rise, 3 volts drop. So I will have a remaining of 7 volt drop across the resistor. Okay. So now the voltage across the resistor has decreased from 10 volt to 7 volt. Therefore, the current through the resistor will also decrease. So the current at some time t1 will be now 7 divided by R, which was previously 10 divided by R. So now you see the current has decreased. So if the current decreases, the rate at which the capacitor will be charging will also slow down, because capacitor is a bucket. If you put more water, it will fill up more rapidly. If you put less water, it will fill up slowly. So that's what's happening to the capacitor. Now that we have decreased the current, the voltage of the capacitor will increase slowly. Anyways, the capacitor will still be charging. After some time, the capacitor voltage will reach, let's say, 8 volts. Then the voltage across the resistor will be 2 volts, which will mean the current will be very small. And a time will come at, let's say, at t equals to some value, tf maybe, some final time, let's say. And at that point, the capacitor has reached the voltage of the supply, which is 10 volts. So in that case, the circuit will look like this. We will have this capacitor, the voltage source, sorry, 10 volts here. Capacitor is also charged to 10 volts. So KVL says that the voltage rise is 10, voltage drop is 10. So therefore, the voltage drop across the resistor will now be 0 volts. And if the voltage drop across the resistor is 0, this means the current, which is equal to 0 divided by R, the current in the circuit will also be 0. So this circuit is now going to look like an open circuit. So therefore, we say that when we place a capacitor in a circuit, initially there is a current flow, but once the capacitor is charged, then the circuit is an open circuit because the capacitor looks like an open circuit. So if I want to draw how the current will look like as a function of time, so you see our initial current was 10 divided by R. So this was our initial current, 10 divided by R. And from that point on, the current was decreasing until it reached 0. Okay, so the current will decrease like this, which looks like an exponential decrease. And we will see that in the future videos. So the current through the circuit will look like this. And let's say this is some time, we will call it 5 time constants later on. After this 5 time constant time, we can say that the transient has passed. This time is called a transient because the waveforms are changing. And after the transient is over, it's a steady state. And in the steady state, we will say that the capacitor is fully charged and it is an open circuit now. So this is the current through the capacitor. And at the same time, if I plot the voltage across the capacitor, V, so we can say that initially the voltage was 0, and after the transient was over, the voltage was 10 volt. So the voltage will rise from 0. Initially, it will increase rapidly because the current is large, but then the increase in the capacitor voltage will slow down because the current is decreasing. And finally, it will reach a fixed voltage of 10 volts because we have applied 10 volts as the battery. So the capacitor voltage will reach to 10 volts after 5 tau. Tau, for now, we can just say that the tau is the product of R and C, but we will look into that in some future video. So 5 times RC is, well, RC is the time constant, which we call tau. So the capacitor voltage will go from 0 to 10. Okay, so now This transient is very quick. It happens very fast. So we do not have a chance to actually see this very easily. To give you an example, if in this circuit my resistor was, let's say, 1 kilo ohm and the capacitor was, let's say, 1 microfarad, then my time constant tau would be 1 kilo times 1 micro. So that would be 1 millisecond. So the time constant will be 1 millisecond and 1 millisecond, and the 5 time constants, of course, 5 time constants would be 5 milliseconds. So within 5 milliseconds, the capacitor will be completely charged and the transient will be over. And if I use a multimeter to measure this, the multimeter will not be able to give me any of those details. It will just give me the steady state that the capacitor is now charged and there is no current in the circuit. Now, I think we are in a position to study a very simple circuit which involves a couple of capacitors and, a couple of resistors and a capacitor. So let's study this circuit first. I have a voltage supply of 10 volts and I have these two resistors and one capacitor. The supply voltage is 10 volts and the two resistors are both 1 kilo ohms and this one is also 1 kilo. So let's say this is R1 and this one is R2. Now we want to see that after the transient is over, I want to see what will be the voltage across the capacitor. Let's say find the capacitor voltage VC. So I want to find that. Now you can think about it. Initially the capacitor will be discharged. So we will assume that the capacitor is discharged. So the voltage across the capacitor will be 0, which will actually short the 1 kilo ohm resistor. So it will look like the 1 kilo ohm resistor is not there. The current will flow through resistor R1 and it will charge the capacitor C. Okay. And as the capacitor is getting charged, it will develop a voltage across the capacitor, which will be the same voltage across resistor R2. And because of that, there will be a current I2. So let's say this is I1 and this is current I2. So there will be a current in resistor I2. And the capacitor voltage will keep on increasing and increasing until it cannot increase any further. Okay. And when that happens, the capacitor current will go to 0. You see, this is the current in the capacitor, and let's call it IC. So you see, when the capacitor voltage becomes constant, then this means there is 0 current in the capacitor. And you can now think of it that this is your bucket and this is the capacitor voltage VC, and it's not changing. So if it's not increasing, it's not decreasing, this means we are not pouring in any water or we are not taking out any water. So this means there is no current in the capacitor in the steady state. So in the steady state, the current in the capacitor goes to 0. So therefore, we can say that now this capacitor will look like an open circuit. And if I want to draw the circuit now, where the capacitor is an open circuit, so the circuit will look something like this, that I have an open circuit over here, and I have these two resistors of 1 kilo and 1 kilo. Okay, so the capacitor is now an open circuit. Now, this is an open branch, so therefore the current here is equal to 0. Current is 0, right? When the capacitor is charged, it's in the steady state. The voltage across the capacitor is not changing. Therefore, the current must be 0. So the current in this is 0. So now the current that flows in R1 and the current that flows in R2 must be the same, correct? Because they are now in series circuit. They are in series. So all of the current I1 will flow through the resistor R2. So this will also be I1. So both of them will have the same current. Now both of them have the same current, both of them have the same resistance. So by VDR, we can find that the voltage drop across these two resistors will be equal, and that will be 5 volt and 5 volt. And you can see that this will satisfy KVL, 10 volt rise and 10 volt drop. So the two resistors will have equal voltage. Now this resistor, R2, is in parallel with my capacitor, correct? It's in parallel. And because the voltage drop across any copper wire is 0, so therefore the voltage at this point is 5 volt and the voltage at this point is 0 volt, right? This is my reference where we assume that the voltage is 0 volt. So now you can see that the capacitor is open circuit, but the capacitor voltage is 5 volts, not 10 volts. Okay, so you see in this circuit, the capacitor will get charged, but it will be charged to 5 volt, not 10 volt. And the reason is that the two resistors R1 and R2, they create kind of a voltage divider, which makes the voltage across R2 that maximum it can be 5 volt. It cannot be more than 5 volt. And that's the voltage which will be in parallel with capacitor C. So therefore the capacitor will be charged to 5 volts. Now let's say I have this capacitor which is charged to 5 volts. And now I take it out of this circuit. Okay, so if I take it out of this circuit and the capacitor will stay charged, it will still carry the 5 volts. So the capacitor will now look like this, that I have a capacitor which is charged to 5 volt. And now if I connect a resistor to this capacitor, so I have 5 volt and now connect a resistor, and this capacitor will now produce a current I in the circuit, okay? And whatever the voltage is across the capacitor, that voltage will be dropped across the resistor. So initially it will be 5 volt and then it will slowly decrease because the capacitor is discharging. So the energy stored in the capacitor will be used to produce a current in the resistor. If I want to plot this current as a function of time, so the current in this circuit would be 5 volt. So at t equals to 0, it will be 5 divided by R, right? As you can see, 5 volt across the resistor, that will be 5 divided by R, and then it will exponentially decay and go to 0. So the capacitor will eventually, the current will eventually approach 0 amperes. Similarly, because the current is leaving the capacitor, therefore the capacitor voltage will decay exponentially. So it will start with 5 volt and it will decay exponentially. Right now we are just plotting these curves without any quantitative results. We are just giving the trends that we should expect. Later on, when we study RC circuits, then we will be able to find the exact numbers, that how much time it will take for the current to go from initial value to, let's say, 1% of the initial value. So we will be able to calculate exactly what will be the current at any specific time in the circuit. Next, I want to consider a circuit in which I have more than one capacitor and more than one resistor, and we would like to calculate how much energy is stored in the capacitors. So the circuit looks like this, that I have a voltage source and a resistor, one capacitor parallel to this resistor, and then I have another capacitor, let's say, and a resistor. This is our reference. The voltage is 9 volt. The voltage supply is 9 volt. Both of the capacitors, C1 is 1 millifarad and C2 is also 1 millifarad. So both of them are 1 millifarad capacitors. This resistor is 1 kilo ohm and this resistor is 2 kilo ohm. So they are slightly different. Now I want to solve this circuit and I want to find out how much energy is stored in each capacitor. We will not be concerned about the transient. Okay, so calculation of the transient is beyond the scope of this course. Here we will only study the steady state. In the steady state, we can assume that both capacitors are charged to the voltage that they can maximum get charged to. So once these voltages reach their maximum value, and then we know that because the V across the capacitor is 1 over C integral of I dt. So if V is not changing, this means that the current is equal to 0. There is no current that flows in the capacitor. We can also see this from the other equation, that I is equal to C times dV by dt. If the voltage is not changing, then this dV by dt is equal to 0 because it's not changing. And if that is 0, then it means that the current through the capacitor is 0. So the point here is that once we are in the steady state, the current in the capacitor is 0, which means the capacitor will look like an open circuit. So now let's reconstruct this circuit with the two capacitors being open. So if I say that both of the capacitors are open, then my circuit would be very simple. I will have 9 volt, 1 kilo ohm resistor and 2 kilo ohm resistor. and I have an open circuit over here, and I have an open circuit over here. So these are the two capacitors that are now open. Both of them are 1 millifarad. So we can ignore the paths that are open. So now I have a simple series circuit of two resistors. One is 1 kilo, the other one is 2 kilo, and 9 volts will drop. So by applying VDR, the voltage divider rule, I know that the voltage drop here will be 3 volt, and the voltage drop here will be 6 volt. So you see 6 plus 3 has to be equal to 9, and also the voltage across the 2 kilo ohm resistor should be twice the voltage across the 1 kilo ohm resistor. So therefore I will have 6 volts here and 3 volts here. So that's very easy to find. Now based on this information, I see that the voltage across the capacitor C1, so let's call it VC1, is 3 volt, because the capacitor C1 is in parallel with the 1 kilo ohm resistor. So whatever is the voltage across the 1 kilo ohm resistor, that will be the voltage across C1. So therefore VC1 is 3 volts. So if I know the capacitance and if I know the voltage, I can easily find the energy stored. Anyways, this is the voltage across the capacitor C1. Similarly, the voltage across the capacitor C2 is VC2, and that should be equal to 6 volt, because that capacitor is in parallel with the resistor 2 kilo ohms. So now that we know both capacitances and both voltages, the energy stored in the capacitor C1 is E1, and that is half C1 VC1 square, and which is equal to 1 times 1 millifarad, so 10 to the minus 3, and then voltage is 3, so 3 square is 9. 3 square is 9. Therefore, the energy stored in the first capacitor is equal to 4.5 millijoules. Right? 9 divided by 2 is 4.5. 10 to the minus 3 is milli, so that's 4.5 millijoules. Similarly, the energy stored in the capacitor number 2 is half C1 C2 VC2 square, which is half times 1 milli, 10 to the minus 3, times 6 square, so that is 36. Now 36 divided by 2 is 18, so that's 18 millijoules. So the energy stored in the second capacitor is 18 millijoules, and this one is 4 millijoules. So we can easily find how much energy will be stored in each capacitor. A couple of other points that I quickly want to make is that what will happen, or how can I find the equivalent capacitors if I place capacitors in series or in parallel? So let's take a look at capacitors in series first. If I connect a circuit like this in which I have two capacitors in series, so if we do this, now I want to find the equivalent capacitance of both of them, both these capacitors connected in series. So this is C1, this is C2. So I want to construct a circuit which will be equivalent to this, but instead of showing two capacitors, we will have one capacitor and we will call it C equivalent. And if it's equivalent, the amount of current I would be the same, and the source voltages are the same as well. So this one capacitor will represent the series combination of the two capacitors. So that's what we are looking for. We can easily assume that the both capacitors C1 and C2 were initially not charged, so the voltage was 0 at time t equals to 0. Then the voltage across capacitor C1, I will call it V1, that should be equal to 1 over C1 times the integral of I dt. Similarly, the voltage across capacitor C2 will be 1 over C2 times the integral of I dt. The current I is the same that flows in both capacitors because they are connected in series. If two components are connected in series, they have the same amount of current that flows through them. All right, so now we can say that I have a voltage V1 over here, and I have a voltage V2 over here. KVL can now be applied, and KVL will say, KVL, Kirchhoff's voltage law, says that the voltage rise in a loop should be equal to the voltage drop. When I go around this loop, voltage rise for me because I'm moving clockwise. So the voltage rise is the source voltage, Vs. So that's my voltage rise, and the voltage drops are V1 and V2. So that's V1 plus V2. We have a video on KVL. If you are not familiar with KVL, please watch that video. Now, V1 and V2 we already calculated, so therefore Vs is equal to 1 over C1 times integral of I dt, plus V2 is 1 over C2 times integral of I dt. Therefore, integral of I dt is the common factor among both of them, so I can say 1 over C1 plus 1 over C2 multiplied by integral of I dt. That is Vs. So this is the equation that I get from my original circuit, right? From this circuit. The equation that I will get from my equivalent circuit, it will be equal to, you see, capacitor and the voltage are connected in parallel. So therefore, the voltage across the capacitor will be equal to Vs. So therefore, I can say that Vs is the voltage across the capacitor is equal to 1 over C equivalent times integral of I dt. So this would be my equation from my equivalent circuit. Now, all we need to do is to compare these two equations. So you see, what is C equivalent? So C equivalent is this quantity in the parentheses, right? 1 over C equivalent. So therefore, I can now say that 1 over C equivalent is 1 over C1 plus 1 over C2. So this is our proof of capacitors in series. So when you have capacitors in series, the equivalent capacitance is actually calculated using this way. And this is similar to a resistor, but you would notice that this is the combination of resistors in parallel. So parallel resistance, the way we calculate that is the same method for calculating series capacitors. Finally, I want to see if I have capacitors connected in parallel. So to simplify, I will assume that I have two capacitors that are connected in parallel. As you can see, they have the same voltage across them. This is my capacitor C1, this is C2. I have a current source this time, Is, which will produce a current Is, but then this current will divide into two pieces. This will be I1 and this will be I2. And I want to construct an equivalent circuit where I have the same current source, but instead of having two capacitors in parallel, now I have a single capacitor and I will call it the C equivalent. Okay, so that's my equivalent capacitor. The current source is Is as before. My original circuit will say that a current Is comes into this node and then it divides into two pieces, I1 and I2. Correct? So I can apply KCL to this node, which says the current that enters the node should be equal to the current that leaves the node. So the current that is entering the node is Is, and the currents that are leaving are I1 plus I2. These are my two currents that are leaving. As we know, if I know the current, then the current through a capacitor is equal to C times dV by dt. Okay, so Is is C times dV by dt. Now I will say that this left-hand side is actually my equivalent circuit because the current here is Is, which is the same, and it flows through the capacitor C equivalent. So I can say that Is is actually C equivalent times dV by dt. I1 is the capacitor C1, so I have C1 times dV by dt, and I2 is C2 times dV by dt. Now you would see that both C1 and C2, they are both connected in parallel. So therefore the voltage across them is the same. Similarly, the equivalent circuit should produce the same voltage. If it produces a different voltage, then they are not equivalent circuits. So therefore the voltage in the equivalent circuit will also be the same, which is shown like dV by dt. So all these derivative terms will be equal. So therefore we can divide both sides by the derivative terms, and we will be left with C equivalent equals to C1 plus C2. So this is the final result for two capacitors in series. So if you have three capacitors in series, capacitors in parallel, if you have three capacitors in parallel, it will be C1 plus C2 plus C3, and so on. That was it for today's video. And if you liked the video, please subscribe to my channel, and I'll see you next time. Bye for now.